my dear students, now I will discuss about quality factor. Quality factor is a ratio of resonance frequency to the bandwidth. You have been known from the previous slides that I have shared to you that quality factor is omega naught divided by bandwidth, and the ratio of resonance frequency to the bandwidth is quality factor. That is the sharpness of response curve could be measured by the quality factor Q. And later I will discuss how that you can get the point, just a look at it. There's a Q, that is omega naught, and that is omega naught L divided by R. Why that is omega naught L divided by R? Here you can see there's a omega naught and there's a beta. So beta is equal to R by L in RLC circuit, series RLC circuit. So just put the value from there. You can get these R and L. Okay. So that is going to be a very interesting part. The R and the L. That is R by L, and just put the value from here. We can get it. So how can we get the high quality factor? The high quality factor, it is to be a high quality circuit when its quality factor is equal to or greater than 10. So that is the condition of getting the high quality factor. So for a high quality circuit, high Q circuit, that have to be greater than 10. It's greater than. And the half power frequencies are, for all practical purposes, will be symmetrical around the resonant frequency, and can be approximated as omega 1 approximately equal to omega naught minus beta by 2 and omega naught plus beta by 2. That is an approximate. That means in high quality factor, the half power frequencies are symmetrical, means they are in the same distance of quality factor. If that is a frequency axis, if that is omega c or omega naught as cutoff frequency, the omega 1 and omega 2 will be divided by will be just differenced by the cutoff frequency equal distance. It will be equidistant to each other. That is known as symmetrical to each other, and the distance will be the half of the bandwidth. As we know, the bandwidth beta is equal to omega 2 minus omega 1. The difference between that is upper bandwidth and that is lower bandwidth. Upper bandwidth minus lower bandwidth, we will upper frequency minus lower frequency, we will get the bandwidth beta, and that is the distance. And if the quality factor is higher than 10, that means it is a high quality factor. The condition changes all the equations, and we come up to know that the distance between these two will be beta by 2 and beta by 2. So we can find out omega 1 and omega naught by omega 2 by it. Omega 1 is equal to with respect to cutoff frequency minus beta by 2 and omega 2 cutoff frequency plus beta by 2. Quality factor versus bandwidth. The high value of quality factor, smaller the bandwidth, higher the selectivity. That means if the quality factor is higher, the selectivity is the greatest. Selectivity of greatest means at the lower bandwidth you will get the higher quality factor. That means you get the good kind of selectivity that could select the frequencies from here. And as the bandwidth is the higher quality factor, lower the bandwidth, so it has a good quality and also has greatest selectivity. That means the quality is high, means selectivity is the selectivity also will be always greater. That means the pickup, because here you can see the value gets maximum, the amplitude gets maximum if it is an axis of voltage or current, so you will get a maximum out of it. Okay, that is known as the greatest selectivity. And if the lower value of a quality, then the larger the bandwidth will be larger. Here you can see the bandwidth is larger, but the selectivity is least. Okay. Next, what is the maximum power dissipated? We can find out the maximum power. The average power dissipated by the RLC circuit is P omega naught. That means in the power in cutoff frequency is known as average power, and we can get the equation by half I square R. Half I square R. How that we can measure? We know that at omega naught maximum current passes through. Maximum current passes through. That means I maximum. Is it right or wrong? That is right. At cutoff frequency. Okay. What is the relationship between I RMS and I maximum? That means when you want to find out the average power, you have to calculate the RMS value. That means IRMS. IRMS is particularly known as 1 by root 2 of I maximum. I maximum divided by root 2, and you just square the term in both sides, you will get the factor half I square R, where I is maximum. If the maximum power dissipated at resonance, we can get, how can we get the current? Okay, we can get the current, the V maximum divided by the resistance, okay, the I maximum. Then put the value from here to there. You can also maximum power dissipated get Vm square divided by R, same as here. So there are power dissipated at omega 1 and omega 2, that means the half power frequencies. There are certain frequencies where the dissipated power is half of the maximum power. That is known as the half power frequencies. How can we get the half power frequencies? Just look the sketch I have drawn here. That is the sketch of a resonant circuit characteristics of frequency or angular frequency is omega, frequency versus voltage or current curve. As we know, at cutoff frequency FC, maximum current or voltage passes through to the circuit IM in that position. So the curve runs through like this. Whether there is high quality factor or low quality factor, that doesn't matter, but the matter is that the curve will look like this. Okay, largely look like this. If it is a low quality factor, that will be a greater bandwidth. If it's a high quality factor, that will be lesser bandwidth. So at I maximum, that will possess at I maximum will be possessed at resonance. That means here XL equal to XC. Okay, that condition is resonance condition. After that, we have to find out the RMS value. That means to find out the average power of the circuit. Okay, as we know that I R M S is equal to 1 by root 2 I maximum. We are calculating with respect to current, that will be voltage, that can be voltage, so that will be any kind of parameters that is related to amplitude you can add here. But IRMS is 1 by root 2 I maximum. Then the curve will go through like this. As we know, 1 by root 2 means 0.707 IM. That means it will be approximately 70% of the value. You can get 70% of the value, and that will be cut off like this. In that position, the total sketch, the total curve will be cut down into 2 points, 2 equal points. In this point, this fashion, there is another point in that fashion. So that will be denoted by F1 and F2. As we know that average power is the half power of maximum power. Average power is half power than the maximum power, and it is also been calculated in RMS situation. So we can easily call upon that omega 1 and omega 2, or F1 or F2, are the half power frequencies. And in that condition, these two powers in that particular two frequencies, there are same current. There is no change in currents, just two different frequency. They possess two different frequency but same current, and there is the RMS current that you get. And this RMS current at that position, you can just you know that that will be half V square divided by R, and this V is RMS. So just put the value of RMS, that means Vm is equal to Vm divided by root 2, as like I have told you that RMS is equal to I 1 by root 2 Im. You can get this equation by that too, because in that situation the power is half. Okay, the power is half. So half of the power, V square R, is the power. The half power frequencies are, this is the half of the half power frequencies. After the calculation you will get this. So there are an example of finding out the resonant frequency, half power frequencies, and bandwidth, amplitude of current at omega naught, omega 1 and omega 2. There is a series resonance circuit where resonant frequency is omega naught, and here you can see that half power frequencies are omega 1 and omega 2, bandwidth is beta, and you have to find out the amplitude of current. How can you find it out? It's as simple. First of all, take R, L and C. Okay, R is 2 ohms, L is 1 milliampere, C is 0.4 microfarad. So first of all, find out the resonant frequency omega naught. Omega naught is largely equal to this equation 1 by root over LC at resonance. Okay, it's a very common equation. Put the value of L and C. 0.4 micro means 0.4 10 to the power minus 6 farad, and 1 milli means you have to put the milli 1 into 10 to the power minus 3. So 1 into 10 to the power minus 3 into 0.4 into 10 to the power minus 6 micro means minus to the power minus 6 root over this value. You can find out the resonant frequency. The half power frequencies, there are some equations I have told you in previous slides, omega 1 and omega 2. If it is a high quality factor, you can largely say that omega 1 is equal to omega naught minus beta by 2. You can find the beta from here. As you know from bandwidth, beta is equal to omega 2 minus omega 1, and for from this, last of all, you can calculate the beta from here and put the value and find out the bandwidth and amplitude of current.